All right, so let's talk about higher degree of polynomial functions, starting with cubic functions. So remember, for linear functions and quadratic functions, there are some details that you had to remember regarding the equation, the coefficients, the degree, and everything, right? And the graph of the function. So when it comes to cubic functions, there are some relations between the coefficients and the graph as well, but it's not as many as quadratic functions or linear functions. Well, to be honest, the only thing that we can actually say about the graph after just looking at the equation of the function is that the constant value, right, is the y-intercept for obvious reason, and that the a, whether it's positive or negative, will determine how your function will behave as x gets large or very small. So technically, if your a is positive, well, for positive leading coefficients, what you need to remember is that your function will be rising as it goes to the right. So it rises to the right, and what happens to the left then is that it will fall. So technically, you will have a function that rises to the right but falls to the left. Hence, what you will be getting is basically this kind of graph or this type of graph. These are the only two types of graphs that you will see for positive a for a cubic function. Okay, now for negative a, your function will fall as it goes to the right, and it will rise as it goes to the left. It's the opposite way as the above, right? So you will be getting a graph that goes like this or that goes like this. Remember when we talked about polynomial functions for the general terms, right? There was something that I mentioned there, something called turning points. We didn't have to really talk about turning points when it came to linear function because there isn't any. And for quadratic function, well, there is only one turning point, the vertex. Now, for cubic functions, well, sometimes there is no turning point, but sometimes there are two. Do you have any idea what a turning point is now? Linear didn't have any, quadratic had exactly one. Cubic might have none or two. Well, maybe you've already guessed it. These are the turning points. Basically, turning points are where your function rises, right? Then falls, or when falls, then rises. When it changes its style, there will be a turning point. So here, falls, then rise, right? So first turning point and rises, then falls. Second turning point, that's all. So is there anything else that we can say? I mean, well, we can calculate the values for zeros as well. You may let that is equal to 0 and try to factorize it and look for the zeros and mark your zeros as well. But there are no line of symmetry, nothing else that we can actually determine by just looking at the coefficients, except for the y-intercept and how the end behavior behaves depending on your leading coefficient a is. But it's actually quite important, guys. Sometimes you need to look at the graph and find out what the degree or what kind of leading coefficient that the graph might have. So remember, remember that the degree for cubic is 3, right? Degree is 3, and that the graph behaves, right? Rises and falls if coefficient is positive, and the other way around if the coefficient is negative. Okay, now let's talk about quartic functions now. Quartic functions has a degree of 4. And as above, if your a is positive, then it will be rising as it goes to the right. But funnily, it also rises to the left. If your leading coefficient is negative, it falls and falls. Isn't that interesting? Okay, now, so the types of shapes that we might have is this and, well, something like that. Or upside down, or something like that. As you can see, this looks like a parabola, right? Well, for quartic functions, we could have a parabola, right? And as well as these kind of shapes as well. Let's talk about turning points. Well, how many turning points do you see here? 1. What about here? 1, 2, 3. Okay, what about here? Same, right? So number of turning points, well, equals to 1 or 3. Well, what about here? What was the number of turning point here? Remember, guys? It was 0 or 2, right? 0 or 2 here, 1 or 3 here. Remember that? So again, with quartic 2, there are not much that we can actually say by just looking at the equations. We can actually calculate the values for zeros and mark your x-intercepts as well. However, but for now, we can only tell the general shape of the graph and where the y-intercept is going to be. Okay, now, so we can continue, just talking, we can continue to talk about like other polynomial functions as well. But guys, honestly, we'll be just repeating, this like if A is positive and if A is negative, right? So let's just talk about like the general rules that you must remember when it comes to polynomial equations and its graph. Okay, now, before we move on to like the general rule, I want you to just like think once. Okay, do you remember what your linear function graph looked like? I mean, it was a straight line, right? It was like either this, if A is positive, if slope is positive, right? Or it went like this, if your slope is negative. What about your quadratic function? It went like concave upward, just like that, right? Or downward, depending on your A. And as you can see, for linear, right? For linear, where the degree equals to 1, had this or this type of graphs. For quadratic, for degree of 2, right, had this or this types of graphs. Do you see what I'm trying to point out? Well, actually, I want to point out that if the degree is odd, 1 or 3, right, then when one part rises, the other part falls. Okay? You see how when one side rises, the other side falls, right? But for even degree polynomial functions, when one side rises, the other side also rises, right? When one side falls, the other side also falls. Hence, if your function graph behaves in a certain way where both sides goes up, right? Then we can actually say, without knowing the equation, right, that the degree of this function must be even. If the function behaves the opposite directions, right, toward the end, then we can at least say that the degree is odd. Okay, so let's talk about the generals then. So, well, it's not just the degree that we can tell. Remember, I counted the turning points? Knowing the turning points, it helps you understand what the equation is going to be like as well. I mean, it can't really tell you the exact values, but at least we can, tell whether the leading coefficient should be, well, positive or negative by looking at the behavior. And also, there is a direct relationship between the turning point and the degree as well. And also, leading coefficient and degree are the only two things that we can determine. However, it's really important that you know it for your SAT subject test as well. So, okay, let's talk about it. So, degree, the relationship between the degree and the turning point, okay, is that if your degree is n, then the degree must equal to the number of turning points plus 1 or 3 or 7. I mean, I know it's a little bit too vague, but actually it's really, really simple. It's just that when you see a parabola, right? A parabola can be given by a function x squared, right? But also by to the 4th power, also by to the 6th or to the 8th. All of this looks like a parabola. You understand? Well, the only difference is that, this will be growing much faster than the other one, right? So anyways, if you have a parabola, then how many turning points do you see? Just one, don't you? So if 1 is the number of turning point, then 1 plus 1, right, which equals to 2, or 1 plus 3, which equals to 4, or 1 plus 5, or 7, or whatever, any odd integers will do, could be the degree of the given function graph. That's what it means. Hence, there's no one answer to it, but at least we know that the degree for this will start from 2, and it will be the every other consecutive even integers from 2 and on. Okay, so one more. Okay, what if we have a function graph that goes like this? How many turning points do you see? 1 and 2. So what will be the degree? Well, the degree will be, turning point equals to 2. So 2 plus 1, so degree could equal 3, or 2 plus 3, degree could equal 5 or 7, right? So we can continue, and we will be getting every consecutive odd integers starting from 3. 3, 5, 7, 9, right? These all could be a degree of a function given by this graph. Okay, now, also, by looking at the x-intercepts, we can actually determine the number of imaginary zeros as well, but we will discuss this a little bit later. Also, this leading coefficient, most importantly, tells you whether your function should rise or fall as the x gets really, really large. So as x gets really large, well, as it goes to the right, your function will have to rise if your coefficient is positive. If your function is falling, it means that your coefficient was negative. So, well, the basic things that you can determine is the degree, looking at the turning point, though there's no one answer, at least we can, figure out what the minimum, degree, it can have. And also, by looking at the direction of the function that it's heading as it goes to the right, we can tell whether the leading coefficient should be positive or negative. Okay, now, let me give you an example. Let's see if you get the degree and the leading coefficient right. So here we go, some random function. We know nothing about this function except that it looks like this. Okay, so if you have to choose which of the following could be the graph, right, of this given function, then what will you choose? Choice 1 that says negative x to the 7th plus b, I'm not telling you what the values are, c plus dx to the 4th, we'll continue on, this is the highest degree. Or the second one, similar, but this is positive, plus b to the x to the 6th plus c times x to the 5th, etc. Okay, here we go. And then lastly, x to the 9th plus b to the, here we go, c x to the 7th. Okay, now, if you have to decide which of the three could be the equation, right, for the given graph, what will you choose? Now, it's rising, okay? It's rising as it goes, to the right. So, the leading coefficient has to be positive, right? Positive leading coefficient. This is out. Obviously, it has a negative leading coefficient, right? Okay, now, of the two, let's see, what can we tell? We know that the degrees are 7 and 9, so if we can count the turning points, we know whether 7 and 9 are okay as the degree of the function, right? So let's count the turning points. 1, 2, 3, 4. There are 4 turning points, right? Hence, the degree, so the degree could equal plus 1, 5, plus 3, 7, plus 5, 9. Oh, there you go. 7 and 9 are okay as the degree of this function graph. Hence, we know that there are two possibilities here, 2 and 3. Since we don't know anything about the rest of the coefficients, you know, for obvious reason, because we actually cannot determine anything further from, you know, the degree other than the degree and the leading coefficient by looking at the graph. So these are the only two things that we can determine. So when it comes to questions that asks about these details, right? The questions are as simple as this. So just remember the simple rules, and you will not have any trouble, you know, selecting the correct equation for the given graph. So let's talk about the zeros now, shall we? Well, zeros are very, very important because that is the value of x that will make the entire function as equal to 0. And it's something that we can actually calculate. It's not something we can just determine by knowing the concept. You need to actually calculate it out. Or if you are using your graphic calculator, you may just graph it. But first of all, when you graph it, guys, the zeros that you are seeing from the graph is the real zeros. I mean, obviously, right? It's real. That's why you're seeing it. These are the two values of, say, -1 and 3, for example. These are the real zeros that will give you a function value as equal to 0, right? And 3 also is equal to 0. So, however, the thing is, are the zeros always real? I mean, okay, technically, I know it doesn't really make any sense. If it's not real, how can we write it? But unfortunately, for math, we actually have numbers that are called imaginary. If you don't understand imaginary numbers, you can actually check out the lecture on complex values. So, you know, then you will understand it a bit better. Anyways, just for now, let's talk about having like two types of numbers. Real, all the numbers that we know, integers, rational, irrational, they're all real, right? Unfortunately, there are other type of numbers, imaginary numbers, which is not shown on the graph because it's not real. However, we may write it. So that's the problem. You need to still look for the imaginary zeros, even though it doesn't exist. And it can be done by calculating it out. So imaginary zeros comes when it comes to an example question with f of x being equal to x squared plus 1. You know that the graph, guys, do you remember transformation? Plus 1 means what? Having to move your function up by 1 unit, right? So this will be given by a perfectly symmetrical parabola about the y-axis with an y-intercept of 1, right? So as you can see, this does not have real zeros. It doesn't touch the x-axis. However, if you try to solve it, you will be getting x squared is equal to -1, and x then will equal to plus or minus positive or negative square root of -1, where, you know, actually until the level of algebra 2, we usually stop, you know, right here. But for pre-calculus, we continue on and say this equals to positive or negative I, because square root of -1 is an imaginary number I. So quickly, if you see 2i, it basically means 2 times square root of -1. Okay? So we have this special, you know, I that can actually help us write down what an imaginary zero is. So though it's not really shown in the graph, we can still calculate for it. And the thing is, if the degree, okay, the degree of the function should equal to the number of real zeros plus the number of imaginary zeros that the function has. So technically, you see how this has two imaginary zeros, positive I and negative I. There are two, right? Hence, the degree is 2. It's a match. Okay? So for example, if you see say this is a cubic function. As you can see, this is a cubic function, so this has a degree of 3. Then, you see how you have only one real right here, right? that means that you will be having 2 imaginary, because the total sum of for the number of real zeros and imaginary zeros should equal to the degree. That's why the real, if there's only one real, you should know that there are 2 imaginary values. So, you know, it's really, there are further things that you need to understand if you want to go deeper. But for your SAT subject test, that's all you need to remember. Just remember the number of real zeros plus the imaginary equals to your value n. So if you see a degree of 5 and you only see 1 real zero, then you know that there are 4 imaginary zeros. Except you must be careful. There are special cases. So let's so zeros and the number of zeros and the degree. It's not always asked, but it's pretty popular. Okay, so let's just talk about number of zeros. Remember, guys, for discriminant, b squared minus 4ac being equal to 0 gave you a quadratic graph that has x-intercept, right? Touching the x-axis like this. So it seemed like we only had 1 real zero. However, this actually is translated properly into 2 equal zeros. Okay? Well, technically consider this. When you have a function graph that looks like this, it's usually given by, we'll say x minus 2 squared, for example, okay? What does that mean? It means that x minus 2 times x minus 2 is given, so that your 0 equals to 2 and also 2. As you can see, we have 2 of the same. And whenever that happens, this happens. Okay? So guys, please remember, when you are just mining the number of zeros by looking at the graph only, be careful, because when the function is tangent to the x-axis, okay, that means that there are 2 of the same zero, not 1. Well, technically it's 2 or 4 or 6, but anyway, for SAT level, just remember that there are 2 zeros, 2 equal zeros, okay? And when it's passing through it, then it's 1. Consider this as 2 of the same, this as 1. Okay, so don't get confused. So if you have a degree of 3, and if you see this shaped graph, okay, tangent to the axis once and passing through it once, right? You might consider this as 1 and 2 real zeros, but it's not. It's 1, 2, and 3. So this says 3 real, hence no imaginary. As long as the function has a degree of 3. Okay? Since the sum of this and this should equal to the degree. So remember, tangent to the x-axis means double zero. Don't forget that. Okay, so there are relationships between the degree and the turning point, as well as the degree and the imaginary zeros as well. Okay, so before we end, let me just tell you one more thing about imaginary zeros. Imaginary zeros are special because they come in pairs. Meaning you will never ever see a function having 1 imaginary zero. You will always see 2 or 4 or 6. They come in pairs. They come in pairs by this rule. So if you have a imaginary number, complex number, a plus bi, right? So if this is a 0, then the conjugate, you know what conjugate means? Having a different sign right here in front of the radical, okay, is another 0. So given a imaginary number is a 0, right? You know that there is another one that has to be a 0. So for example, if 2i is a 0, then negative 2i is a 0. One more, if 1 plus 2i is a 0, then 1 minus 2i is a 0. Negative 3 minus 5i is a 0. Then negative 3 plus 5i is a 0. So just simply change the sign in front of the imaginary part of the number. Okay, the signs change, so they always come in pairs. So you will never have just 1 0. So let's talk about converting, setting up an equation, knowing the zeros only. Remember how I told you that you need to be able to do, get the zeros from an equation, but also you need to be able to get the equation from the zeros as well, right? So let's just talk about like quick example before we end today. So say that there is a function that is cubic. So cubic function is given with leading coefficient of what? To make things a little bit easier. Leading coefficient equals to 1. And if the zeros are 1 and say 3i, then what is the equation for such function? Okay, now remember with quadratic function in the previous lecture, we talked about how zeros and factors are related. If 1 is given as a 0, okay, then it means that if 0 was given as 1, then there must be a factor for that function given by x minus 1. If 3i is a 0, then there must be a factor that is x minus 3i. Okay, now it's a cubic functions. For cubic functions, we need to have like x cubed. That's 2 of them only. We need 1 more. So where is the third 0? Guys, do you see the third 0? You don't see it, right? But we know that there should be a third one because we know the imaginary 0 conjugate rule. Where there is a 3i, there must be negative 3i, right? Even though you don't show it, you need to know it. Hence, there is a third 0, negative 3i. So finally, x plus 3i is a 0. Well, from here, we could just factor, just multiply the factors. So x minus 1, x minus 3i, x plus 3i. Let's multiply out the latter 2, which will give you x squared, plus 3. I'm just doing a plus b, a minus b product. I mean, you can expand it out if you want. And multiply that by, by the way, negative 3i times 3i is negative 9i squared. But guys, remember that I squared is technically negative square root of negative 1 squared. So I squared equals to negative 1. If you didn't know, remember that. And anyways, so if you expand the entire thing out, you will be getting x cubed minus x squared plus 9x minus 9. And this will be the function equation, based on the information given. So what is that one thing that we have to be careful, guys, here is the negative 3i part. Without knowing this, there's no way you can get this. Okay? All right, so thank you for listening today, and I'll come back with more functions next time.